Welcome to NPTEL Power System Protection course. In module 4, we will talk on directional relaying. In this lecture, we will see how directional relay is being applied in different protection schemes, the basic protection philosophy for directional relaying, and there are different ways to address the directional relaying perspective. We will go one by one. Today, we will talk about the phase quantity based directional relaying principle. Before going to the directional relaying, we will see the need of directional relaying. How does it help in protection schemes? So, if you see this simple system, now as compared to earlier cases, we have sources at both the sides. So, this is no more radial. So, power can flow from left to right or right to left. We can think about a tie line connections at transmission level or so. But first consider a single phase system for understanding. We will extend this idea to generic 3 phase system. Let us consider a fault happens to be there at F1 positions between M and N line. So, at that time current will flow from source 1 like this, and also current flows from source 2 to the fault point like this. So, this current, as you know, becomes also very high, and at that time the objective of the protection scheme is that the breaker at this and breaker at this at the N bus must be open, so that the fault is cleared from both the ends. Otherwise, current will flow, and that is not desirable. Now, one may say that we will trip this breaker here from this side also, that means that the load at this also will be hampered. So, from selectivity point of view, for F1 fault here, we essentially say that the breaker at M bus, this breaker and this breaker should trip, that is the desirable things for the protection scheme. However, in case of a failure of the breaker at this point, the backup you can say that breaker here should operate. Now, on this perspective, we see that you can say that if the relay for the corresponding breaker at this point, if you see designated as R M N, the current during this fault as seen by the relay for a fault at 1 second inception, then the current becomes like this, and the current becomes high following that, following through a transient decaying DC component and so. So, this is what for the single phase system for fault at F1, the current which will be observed by the relay at bus M, the R M N, the relay which is being assigned to consider for this breaker. Now, let us come to this another fault at F2 in line M N in the same single phase system. Now, current flows to this fault F2 like this from left hand source and from the right hand source. At this point, the desirable thing is that the breaker this one and this one should be open. Now, how does this relay at M, same relay what we have earlier discussed, how does it see? So, now the current which will be seen, we see here now flows from right to left for this relay, and that is what is shown here, that the current now changes in a different way for fault F2 as compared to F1. So, this is what we see, you can say that for the two fault cases, one in F1 this side and one in F2. Now, if you mark these two, considering assuming that you can say that the corresponding both the faults happen at the same fault inception point 1 second here, this is some simulated data for understanding purpose. So, then if you plot the two currents, fault currents, they become like this, the solid line for the F1 fault and the dotted line for the F2 fault, and both the currents are observed by the relay RMN. So, we observe that you can say that for RMN for F2 fault the current becomes reversed as compared to for the fault for F1, and that is what if we see these two currents, that there is a phase separation between two currents F1 fault for F2 fault. This is what we observe from these simulation plots for the two currents. Now, we can extend this idea to the 3-phase system. So, this is a 400 kV 3-phase transmission network, part of the big network, and this is interconnection 1. So, source 1 and source 2, similar to what we have discussed earlier in the single phase case, and there are two faults F1 and F2, and we are observing the RMN relay. So, if you see that same the corresponding fault, you can say that is being created at 1 second, and then we see that the corresponding 3-phase faults are there at F1 and F2 side, and we see you can say that the corresponding current magnitude for both the faults to be very high. So, what we say from the earlier discussion and this, that in both cases for F1 fault, F2 fault, whether it is single phase or 3 phase, the current magnitude becomes significant, and therefore, the relay at RMN, which should only trip this breaker in case of F1, not for in case of F2, from selectivity point of view, the relay RMN cannot distinguish from magnitude of fault current. So, we have learned till now discrimination of faults in different sections using currents, overcurrent principle. Now, what we see that the overcurrent principle has limitations here, that this relay has to discriminate whether the fault is this side or the fault is this side. Simply a fault is in F1 direction or in F2 direction, accordingly it has to trip or not to trip the corresponding breaker. So, for that we conclude from this discussion that only current magnitude based overcurrent relaying principle cannot distinguish that, and that is what we like to say that for such discrimination directional relaying is required. Direction, what we mean here is the direction of fault. Now, let us see how this corresponding directional relaying is beneficial in discriminating practical systems. Consider a double circuit line and the source or substation side is this and the double circuit line, and it is feeding to different loads or further section. So, we have 4 breakers here. The reason behind if a fault happens to be there in any of the line, let us say circuit 1 at F. So, this breaker 1 and this breaker 3 should be open. So, this line should be out, the other lines to still remain functional. So, that some of the loads here can be still be supplied. So, that is what the benefit of reliability. From that perspective, we say that the breaker 1 and breaker 3 should be open for fault F in the circuit 1. Now, see what happens during that this condition. So, for fault at F, from this source current flows like this, and another path of current is from here to here. So, what you observe, because this is a fault condition, so the current magnitude will be significantly high. So, relay at 1, relay at 2, relay at 4 and relay at 3 all will see large amount of current. So, overcurrent relay we will see that there is higher level of current and it is go for trip decision depending upon the coordination. But what you need in this case, that for this fault only 1 and 3 should trip, not 2 and 4. So, to resolve that, we can use here directional principle. We will have, you can say, a directional relaying at 3. So, what will happen here, if you put, you can say, in addition to overcurrent relay, if you put a directional relay here, then if you see, you can say here the normal flow of current direction for relay at 3 is this, but now whenever a fault happens to be in circuit 1, the current direction is reversed. So, that is what a discriminating function perspective to know the direction of current, and so that gives you the direction of fault, and with that if I put a directional relay here, then that can discriminate that the fault is in the line section or not, and thereby I can say that we can have a coordination at overcurrent level between 1 and 3. So, 3 can trip first, and then you can say that once 3 opens here the breaker, then no current from this side. So, this circuit does not have any current, and this current still may be flowing, and at a later time coordinated with 3, this can be open. So, therefore, we see that in such a considered situation also for the double circuit line or parallel line, the for selectivity point of view directional relaying is a requirement. Now, come to Ringman system, which we have already discussed in overcurrent coordination. Same system we have considered. So, we see here you can say that there are different breakers. Now, let us consider you can say a fault in this line B to C. So, what will happen, that current will flow from this side and also current will flow from this side, but the objective from the protection perspective is that the breaker at here and breaker at here should be open, not the other any other breakers, that is the at primary protection level. So, therefore, what will happen, that this relay at this and this relay at this must see consider this one, but note that all the consider relays associated with the breakers, they will observe large amount of current. So, their overcurrent will trip, and that is not desirable. So, only requirement is that relay at here and relay at here should be there, and this discrimination can be achieved using directional principle. So, we will see consider more details how we can consider use the different directional principles to employ different nodes, different points for satisfying the different protection needs. Directional relaying applications are quite wide. This is being widely used for the distribution and transmission system protections, supplementing overcurrent relay, high speed transmission protection, high voltage level, to supervise distance element, distance relaying. We will see more details on with the distance relay also, used for arc fault protections when selectivity is required, that also we will see along with the transformer protection and so. The common IEEE standard numbers for the directional overcurrent relay is alternating current system is 67, ground directional overcurrent relay is 67 G, and phase based directional overcurrent is 67 P. There are to this 67 directional overcurrent relay, directional overcurrent relay, there are other variants also. We will see consider that later on. Now, we will go to the principle one by one. So, first we will go to consider that phase quantity based directional relaying principle. So, we know we can say that transmission lines are predominantly inductive, R by X ratio is low, and the angle impedance angle is pretty substantially high, 80 degree and above and so. Now, see this system, we can say that as we have already seen source 1 and source 2, and we have already known that for this relay, for fault at F1 and fault at F2, the corresponding current patterns becomes like this. So, we will like to know now how this corresponding relay at this will be able to discriminate whether the fault is F1 side or F6 side. that discrimination is nothing but here is a two class problem for this relay is to be achieved using the voltage and current signals available at the relay point. So, to achieve that let us see consider how we can go with that. So, first as I had mentioned we will go with consider phase quantity based approach and then we will go extend this idea for other options also. So, we see here consider that at Vm at the bus M Vm, that is reference, a fault happens to be in F1. So, current flows from left to right. This path impedance path is highly inductive. So, therefore, the current considered flowing through this relay IMN for fault F1 IMF F1 will be lagging to this voltage at this bus relay bus, and that is what the lagging current. Now, this is that consider the solid line current we talk about. Now, in case of F2 fault, same relay will now see a current flowing from right source to the S point. So, therefore, the relay will sense a reversal of current with respect to the earlier case. So, that is what a reversal of current we are noticing with the dotted line. So, therefore, the reversal of current for F2 becomes this IM F2 and that is what 2 Vm, this will be a leading current. This implies that the relay at here can discriminate this F1 fault and F2 fault using the current, phase current and the phase voltage and the associated angle. In case of F1 the forward fault, we call it as forward fault, forward looking relay for this line protection of M1. For this forward fault, the corresponding current lags the voltage by certain angle, and in case of reverse fault, that is the F2 side fault, the corresponding current noticed by this relay leads the voltage, and that is what the conclusion we have from this slide. Now, going to a 3 phase system, if you see this corresponding fault, you can say that 3 phase fault. So, all faults are involved. So, this is a VA voltage signal, this is the current signal, compute the phasors, then you get the corresponding angle between current and voltage, angle of current minus angle of voltage, because you are taking voltage as the reference VA. We are only concerned now about the phase A voltagization curve, because we are trying to discriminate this direction of fault using phase voltage and phase current. So, with VA as a reference at bus M, the current here lags for this F1 fault. So, the current here lags, and for this situation if you see the corresponding current obtained, you can say is 67 degree. So, angle of IA minus angle of VA, that comes out to be minus 67 degree, that is what the phi angle. Now, when you go to F2 fault for the same 400 kV system, the fault now is a reverse case. So, current flows from here to here, and that is what noticed from this current pattern with respect to this VA at bus M for this relay. So, the angle of IA minus angle of VA, that becomes positive now, as you have already seen. So, we have already done VA, the phase voltage at bus M, and the IA is leading, and the angle comes out to 107 degree, and this phi is a positive value. So, this is the reverse fault for this relay, and that angle comes out to be positive. The way we have computed here, there can be different options also for that perspective. The angle we have computed it, angle of IA minus angle of VA. So, whichever phase is involved with fault, take that current phasor, angle of that current phasor minus angle of that phase voltage will be indicative of the direction of fault. If that angle comes out to be positive, we say the fault is reverse side for the relay. If that angle comes out to be negative, then we call the fault to be forward fault. These kind of principles, directional link principle is being widely used with overcurrent relay as I mentioned, and that is designated 67 IEEE standard number. What is being done in directional overcurrent relay principle, that the decision by the overcurrent and the decision by the directional, we have a AND circuit, and by ending that we decide whether to trip the corresponding breaker or not. So, that means that the trip decision is the decision by the X, the overcurrent, and ending operation and the decision by the directional link. So, that is what we talk about directional overcurrent relay principle, widely used in distribution and at transmission level also. However, this phase voltage and phase current based relaying principle has certain problems. Let us observe this. So, for this fault F1, 3 phase fault in this transmission system, if the fault comes out to be very closer to this one and the source is strong and this line is not long, then phase A voltage here collapses, and that makes substantially having a lower value, and that is what we observe here, that as compared to, you can say that the corresponding other phase voltages, the corresponding voltages is significantly low because of the fault being close to the relay bus. In that case, the corresponding voltage being substantially low because of the other uncertainties and all these things, the phasor value will not be reliable, and therefore, this you can say that corresponding associated angle of the phase A, VA, angle of VA cannot be considered for reliable directional link principle. We know that most of the faults are line to ground faults. So, as already mentioned, phase voltage and phase current can be used for directional link. If you use the corresponding phase voltage for a line to ground fault, the corresponding voltage may be substantially low, and that may not be a reliable option for that one. In that scenario, we have alternatives. So, for that what we do is that we use the quadrature voltage directional elements. What do you mean quadrature here? That because most of the faults are line to ground faults, say a G fault, a J to ground fault, then instead of taking VA, B phase and C phase voltages are sound phases now. So, we can take VBC, then we can get a more reliable, you can say that, directional link solution. So, what you do that to avoid that low voltage situations, the common practice is that for phase A fault, the corresponding operating quantity is IA and polarizing quantity becomes VBC instead of VA. For B, it is IB current and VCA, not the VB. For C phase, this is IC current and VAB, not the VC. I told you that most of the faults being line to ground faults, we can overcome the problem of significantly small voltage for close in fault, which are very close to the relay bus. In that case, if you see this phasor diagram, so this is VA line, this is VB line and this is VC line, here 120 degree. Now, let us say this is AG fault. So, VA becomes smaller and the corresponding IA current becomes significant, and that will be lagging to. This is a forward fault case, as we have already seen in the circuit. So, this corresponding phi, this is a lagging current, and in this case, if you see this is VB and VC, they remain intact. So, therefore, you can say that the corresponding VBC becomes this. So, if you plot here, you can say that at this point origin, then this becomes VBC becomes this. So, we see that now that this IA and VBC, they take this position like this. Many relays, what they can say that do is that they suitably translate this, you can say that VBC to the again bring back this VBC to this VA reference. For that you add, you can say that 90 degree to consider to the angle of VBC. Then the corresponding reference, you can say that voltage becomes in line with VA, and then similar you can say that positive value of phi, negative value of phi, the concept which we have used for, you can say that reverse and forward fault can be equally applied. So, this for that once again I am telling that one of the way many relays do is that once you compute the VBC, add the corresponding angle, you can say that of the VBC 90 degree, then again you can say that you can bring back the corresponding reference to this same reference as the VA, and thereby I can say that you can apply this leading and lagging concept of this current, which will decide, you can say that the direction of the fault. We will see different examples for this kind of applications also. Now, let us, you can say that come to the same 400 kV 3 phase systems, and we have a forward fault F1, and then this we are observing this relay which is assigned for this breaker. So, this is a forward fault and we are observing for this relay 400 kV transmission system. Now, let us, you can say that we see that for a fault, this is the set of voltages, set of currents observed by the relay and set of voltages which is measured by the relay. So, if you see this current 2.04, 0.75, 0.71. So, this clearly shows that this is a phase A to ground fault, and if you see this corresponding phase A becomes substantially low as compared to B and C. So, now the relay will make a judgment to this is acceptable for deciding on the relay or not, phase simple phase, you can say that angle of VA and IA, or it has to go for the polarizing quantity using quadrature component, that is VBC, because this is phase A current. The fault is AG type, phase A to ground fault. So, therefore, what we say here that if the corresponding relay rejects that no, this is not acceptable, then it will be using VBC, which is better option. So, then in that case what you do is that this VBC, whatever angle we have, you can say that we make it 90 degree with that, and then you can say that we compare with IA to compute the phi. So, the phi angle is nothing but you can say that angle of IA minus angle of these combinations, then we get the angle to be minus 67.04 degree, and this angle is negative, indicating this is a forward fault, which is conforms to our simulation for F1 fault. So, this you can say that we see that in case of phase voltage is significantly low. So, the better option you can say that is quadrature component can be used. So, that is why I can say that this is very common, that instead of using phase component of voltage, the relays generally you can use, you can say that take the option of quadrature components, because most of the faults are line to ground faults. But still there is problem that in case in case if the fault happens to be 3 phase fault and close by to this bus M, then all the phase voltages may collapse. Then in case of what is the solution? So, we will look into those kind of issues also later. Now, let us you can say that whatever you have learned how to discriminate forward and reverse fault to obtain the direction of fault, that is why directional laying perspective, which is being used in the different protection schemes. We will take a 9 bus WSC system, and we will check, you can say that in this system how you can say that the corresponding quadrature voltage approach is reliable. We will check. So, we will see, you can say that see only this relay which takes care breaker at here for the line section 8, 9, and also you can say that the other relay will take R2 at bus 9. So, these two relay takes care this line, and how do they see this fault? F1 fault which is internal to this line, and F2 fault which is external to this line 8, 9. So, how do they see? Now, if you see this perspective as we understood, for R1 this F1 fault is a forward fault, for R2 the F1 fault is a forward fault. They take care the corresponding breakers at this bus 9 and bus 8. For F2 fault, the relay at 9 R2 will still see a forward direction, but R1 at bus 8 will see a reverse fault. So, with this you can say that we will see how the corresponding relay will be able to distinguish this F1 and fault as a forward or reverse fault. First case, the fault is AG type phase A to ground fault created at F1 here, and now this relay R1 and R2 they will have measurements for this fault. So, these are the set of measurements for R1 current set IABSC, VABBC. Similarly, for R2 also we have current measurements and the voltage measurements. From there we get the corresponding phasors using DFT, least square or so. Now, we see this perspective, if we see this phase A current is 0.53, phase B is 0.11, phase C is 0.1, this is phase A to ground fault. So, this clearly is being observed here. The VA is low, much lower than VB and VC. In this case also, bus 9 also at relay R2, the corresponding phase A voltage is substantially low, that is what you observe. So, now we will see, you can say that what you can do, I can apply the corresponding quadrature voltage approach. One can use also the phase voltage approach also. So, now if we compute the VBC, because fault is in phase A, compute the VBC. So, VB minus VC, so then we will get, you can say that 191.66 with 178.80. So, these are all system level voltages without using any sensors and so for our easy understanding. Similarly, for R2 for the same F1 fault, the VBC is 196.64 with 176.83 kV VB minus VC. Now, what we do is that we see for these cases, if we take the VA as the reference, I will take the VA as reference minus 87.91. So, make it add plus you can say that 87.91, add all you can say that value to be plus 87.11. So, we shift it, you can say that you rotate it anti-clockwise, then we will get the corresponding VA as a reference. At that time, so we will compensate for all you can say 87.91 degree. At that time, the corresponding VA takes the position of this. You see here, if 87, this is minus 149. So, this current is lagging to VA. Now, you get the VBC 90 degree to that, as such VBC will be 90 degree to lagging to this VA. So, this is VBC position, but as per our you can say that principle, quadrature principle, what will they follow is that angle of VBC plus 90 degree, we say you can say that, and then that you can say that again is being shifted to this VA reference, and then you compare the corresponding IA position. So, angle of IA minus that shifted you can say that VBC, we will compare that and get the phi, and that comes out to be minus 54.63 degree. So, this shows that this minus angle shows that this is a forward fault as observed by relay R1 for this F1, which is correct. Now, we will go to this R2 now. R2 has this VBC to be this, and we draw the phasors, it comes out to be same. So, R2 the corresponding VBC plus 90 degree, whatever VBC plus 90 degree, angle IA we know minus 151.53. So, angle of IA minus angle of this shifted VBC will give us phi, and that comes out to be minus 58.36 degree. So, this minus angle shows again this is forward fault. So, for R2 also this is forward fault. So, the conclusion from these two you can say that R1 and R2 that both are forward, and that means that this is an internal fault, and this is also correctly identified by these two relays R1 and R2 using the quadrature voltage approach. They are able to identify the direction of fault properly. You can try with also simple phase based approach also. Now, I will go to the next fault at F2. As I already mentioned, for fault at F2, relay R2 sees in forward direction, but relay R1 sees this is reverse direction, Let us see how they see through this calculation process. Relay R1 has this set of currents, this set of voltages, R2 has this set of currents and voltages. So, current in phase A is high, current voltage in phase A is substantially low, here also it is lower than B and C. We computed the VBC for between this V minus BC and we computed VBC from V minus BC here. Now, I got the corresponding VBC, VA and IA position like this. Now, note that here for this case the IA takes a position like this. If we compensate, you can say that the corresponding VA to be a reference minus 87.55, A to consider that plus 87.55 to all, then we will be getting, you can say that this IA plus 87.55, 25 plus that. So, this gives you an angle like this. So, this shows that with respect to VA this is leading. When you come to, you can say that, so this concludes that this is a reverse fault. Similar conclusion also from VBC, VBC takes a position like this plus 90 degree. So, again it comes out to be VA reference with an angle of IA. So, therefore, you can say that the IA, the corresponding phi happens to be 120.84 degree. If that is so, this is a positive angle less than 180 degree. So, we conclude that this is a reverse fault. When you come to R2 and this set of measurements and then again VBC becomes this. So, angle of VBC plus 90 degree and then that you can say that the angle IA. So, angle of IA minus this angle gives you phi to be minus 60.33, negative angle, forward fault. So, we see that for R2 this is forward fault and for R1 this is reverse fault and this is correct as we have already mentioned for the F2 fault. So, therefore, these two relays you can say that are able to distinguish the corresponding fault in terms of the directionality successfully using the quadrature voltage component. So, we see that quadrature voltage or simple phase voltages can be applied to that, but they have their own merits and demerits. There are alternative principles on sequence components based approach and so by different numerical relays. So, we will see, you can say that why the corresponding sequence components are able to distinguish the direction of the fault. We will see that perspective and how they can be applied in a better way for directional link principle. We will see more details on the next lecture, but have a see, consider see what happens that the available sequence quantities for different faults. So, for 3 phase fault V1 is present, for line to ground fault V1 is present, for line to line fault V1 is present, for 3 phase V1 is always present. Any measurements at any relay bus will give you the V1. V2 is present for all faults except 3 phase. V0 is present only for, you can say that fault involving ground LG and LLG. I1 for alt, I2 for unbalanced fault and I0 for, you can say that faults involving ground. With this scenario, so sequence component based directional principle are being applied. So, there you can say that having quantities operating quantity is I1 and the polarizing quantity or reference quantity is V1, I2, V2, I0, V0. These quantities can be, you can say that used to produce different relaying principles faithfully. We will see one by one. Because of the transformations from phase quantity to this sequence quantity. So, let us say negative sequence. So, we are getting one pair only instead of VA, BB, BC and IA, IB, IC. So, that reduces the, you can say that the directionality computational perspective. Note that if you do V divided by I put V2 by I2, V1 by I1. So, that gives an impedance form. So, we can use the impedance form and the angle of the impedance is indicative of direction, that we will see in more details in the next class. Thank you.